Okay, so for centuries, you hear these stories from sailors. Giant walls of water just appearing out of nowhere.
Right, these freak waves.
Exactly. And if you were the one reporting it, well, you were likely dismissed.
Pretty much, yeah. Science, or at least the models they used back then, the linear ones, they basically said the chance was tiny.
Like once every 10,000 years tiny. It was just seen as what? Folklore.
Yeah, sailors' yarns. So our mission today is to kind of unpack that. How did we get from myth to, well, measurable fact?
And right off the bat, we should probably clarify something for you listening.
Oh, definitely. We are not talking about tsunamis here. That's a whole different beast.
Right. Tsunamis come from earthquakes, landslides underwater, big geological stuff.
Exactly. These rogue waves, they're different. They're very localized, super high waves generated right there in the ocean by the waves themselves. Complex hydrodynamics.
Okay. So the history then. It really does feel like people were just ignoring the evidence for a long time. Where do we start seeing actual hints?
Well, the skepticism was profound, even with physical clues. Take the MS Minchin, a big cargo ship lost in the North Atlantic back in '78.
Sure.
Completely vanished. But later, they found one of its lifeboats. Now, this thing was bolted down way up high on the stern.
God.
20 meters, that's what, 66 feet above the waterline?
Wow.
And it had been ripped off. Violently. That suggested some kind of force that, well, according to the stats, shouldn't really exist.
And this ties into that whole dismissal thing, doesn't it? The drunken sailor idea.
It certainly didn't help. I mean, we know the shanty is actually about, crew discipline.
Right, not about them hallucinating waves.
But that stereotype, it definitely fed into the skepticism. It made it easier to dismiss genuinely accurate reports from experienced mariners who saw these things.
So when did that skepticism finally break? Was there a specific moment?
There absolutely was. January 1st, 1995, New Year's Day. The Dropner gas platform out in the North Sea, it had instruments, lasers measuring wave height constantly, and it recorded the first officially verified rogue wave.
And how big was this one?
It measured 25.6 meters high, almost 84 feet.
Okay, that sounds massive. But what makes it definitively rogue?
Context. That's the key. You need to look at the sea state around it. Engineers use a measure called significant wave height, or PATE.
Wait, can you break that down quickly? What does that actually represent?
Sure. Aegis is generally defined as the average height of the highest one-third of the waves in a specific area over a period of time. It sort of gives you a picture of the overall roughness, the typical storm conditions.
Got it. So it's like the average height of the bigger waves around.
Exactly. And at the Dropner platform that day, the Aegis was about 12 meters.
Okay, so the surrounding big waves were around 12 meters. But this one single wave hit 25.6.
Precisely. It was more than twice the significant wave height.
Ah, so that's the benchmark.
That's the official definition right there. A wave is considered rogue if its height, let's call it 3 Talker, is greater than 2 times H's less, or 2 H's less.
So Dropner wasn't just a big wave, it was disproportionately huge compared to everything else around it.
Yes, and suddenly it wasn't a statistical ghost anymore. It was real, measured, a physical threat that needed a proper physical explanation because the old linear math just didn't cut it.
Right, so if linear statistics failed, what kind of physics stepped in? How do you get such an extreme energy spike in one place?
Well, the answer is nonlinear dynamics. It gets a bit complex, but the most dangerous types, the really extreme ones, seem to be generated by something called modulational instability. MI for short.
Modulational instability.
Well,
okay. How does that work? Is it like waves adding up?
Not just simple addition. No, think of it more like an energy thief. This instability, which is described by some pretty advanced math, like the nonlinear Schrödinger equation, or NLS. It allows one wave in a group, in a wave packet, to sort of suck energy away from its neighbors. It focuses the energy from the surrounding waves into itself.
Wow, okay, so it grows really tall, really fast by stealing from nearby waves.
That's the idea. It creates this localized, massive spike, and it also explains why they often seem so impossibly steep.
Is there a limit to how much energy it can steal?
Well, there's a theoretical model based on the NLS equation called the Peregrine-Soliton. It predicts this mechanism can create waves with an amplitude up to 3 times that of the background waves.
3 times? Not just double. That explains the extreme nature then.
It really does, that suddenness, that extreme steepness.
So that's one way they form, sort of an internal process within the wave group. Is location a factor too? Are there specific places where this is more likely?
Oh, absolutely. That brings us to the second main mechanism, dynamic focusing by currents.
Okay, how does that work?
Imagine you have strong ocean currents moving in one direction, and then you get storm waves traveling in the opposite direction running into the current. The current essentially squeezes the waves, it compresses them, shortens their wavelength, and forces them to pile up, getting steeper and taller.
So the current acts like a lens, focusing the wave energy.
That's a great analogy, yes. A focusing effect. And there are known hotspots for this.
Where's the most famous one?
Probably the Agulhas Current off the east coast of South Africa. That region is notorious. It's considered the global hotspot where rogue waves happen most frequently.
And these current-focused waves, are they different?
They tend to be a bit longer lived, perhaps, than the ones formed just by the modulational instability. They can travel further.
And the danger. I mean, we talked about the mention. What did these waves actually do to a large modern ship?
It's about extreme localized forces. Engineers talk about hogging and sagging. Imagine the wave lifts the middle of the ship way up, leaving the bow and stern hanging. That's hogging.
Okay.
Or the opposite, the crests hit the bow and stern and the middle trough drops out. That's sagging. Do that suddenly and violently enough?
You can break its back?
Pretty much. You can snap the hull. The forensic evidence points pretty strongly towards rogue waves being responsible for losing at least 22 supertankers and big cargo ships just between 1969 and 1994.
22. That's staggering, which makes it even harder to understand why this isn't a bigger part of ship design.
Well, that's the engineering challenge, isn't it?
You mentioned classification societies like DNVGL. Why aren't rogue waves explicitly factored into general design standards?
It's a real gap. The core issue is that these waves are fundamentally nonlinear and, to a degree, unpredictable events. It's incredibly difficult to assign a neat deterministic probability to them that fits into the standard safety rules.
The old linear statistical way of ensuring safety just doesn't map well onto this complex nonlinear reality.
Exactly. How do you mandate a design standard for something that defies the usual statistical assumptions? It's a tough problem.
So let's pull this together. We've gone from dismissing sailor stories to understanding the complex nonlinear physics. We know rogue waves are real. They happen globally, driven by things like modulational instability and current focusing.
We have the mass, we have the observations. The myth is busted.
Right. Which leads us to the final thought we want to leave you with.
Scientists are increasingly predicting that climate change, global warming, is likely to increase the intensity and possibly the frequency of severe storms and extreme sea states in some parts of the world.
So more intense background waves.
Which could potentially mean more chances for these rogue wave generating mechanisms to kick in.
So the provocative question is, given that escalating risk, how quickly does the maritime industry need to adapt? How fast do we need to move beyond those outdated linear models and build these nonlinear realities into mandatory design standards before another huge ship just vanishes?
That's the critical question facing naval architects and regulators right now. How do you engineer for the unpredictable?